There was a survey that asked, how many credit cards do you currently have? And when we open up this table, we're going to see the results. It looks like we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rows, it looks like, and 10 columns. So it looks like we've got 100 that responded to the survey. I've already opened this up in Excel, and we're asked for the mean of the raw data. So, yes, we do have 100 respondents. Remember in Excel, we can find a mean by typing equals average. And then since this is in column A with the first entry in row 1, A1 colon A100, boom. We've got a mean of 3.09. Standard deviation. This is also a sample, as in the previous video. So the .s after stdev.s for sample, same column, and from 1 to 100, equal sign in front of the stdev.s. Now they want this rounded to 3 decimal places, so that's going to round, because of the 7 after the 3, round up to 1.854. Determine a probability distribution for the random variable. Okay, well, we're going to need to sort the data and then count up how many of each of those scores. It looks like the highest was 10. What else? And then when you find out how much repetition there is, divide by 100, so that we're going to be getting empirical probabilities to fill in there. Okay, so not including what I just did for the we don't want the rows for the mean and the standard deviation. Sort all the rest of that. Yep, the highest was 10. All right, so it looks like we have here, none of them said 0. The lowest score was 1. And there are 13 of them. Dividing by 100, 0.13. And then jumping down to 2 of them. I'm going to erase this, at least temporarily. Two of them, we have it's like 31 of them. So 31 over 100, 0.31. Again, I'm going to erase so that I can be counting from 1. Then I can always undo that if I need it later. Make sure I got rid of all those. Okay, so now we're starting at those that had 3. And there are 30 of them. 30 divided by 100, 0.30. So far, that gives us 74, it looks like. Oops. That. So there should be 26 to go. Check that. Yes, Okay, how many 4s? Looks like we've got 10 of them. 10 divided by 100, 0.1. Also notice it says do not round in the directions, which we haven't had to do anyway. All right. Fives. Looks like we've got 8 there. And then how many 6s? Oops. 8 divided by 100, so 0.08 is what I should have. 6 of them. Only 1 of them, so 1 out of 100, 0.01. 7 of them. We've got 3 that answered that way. 3 out of 100, 0.03. 8 of them. There's only 1 of those. Only 1 of them that said 9. 2 of them that said 10. So 0.01, 0.01, and 0.02. As for the graph of the discrete probability distribution, where X is counting the number of credit cards with scores being counting numbers from 1 to 10, then you should look more carefully. But I remember at the end there that we had something like a 0.02, 0.01, 0.01. Sorry, that was 0.03. Okay, close enough. 0.03, 0.01, 0.01, 0.02. The only place where I'm seeing that happen, anything close to that, is here. Higher, same height with these two, and then something in between. You can look back at the table and try to, and even zoom in on this to make extra sure, but it sure looks like this choice B, which is skewed right, by the way, should be the one. In fact, they asked that. Now, I'm only seeing one highest value there. Let's double check that. There were 2 that were close, but the 2 is the highest. So let's see if they want, has one mode. Okay. Now what we found in part C, they want the mean, and then they're going to ask us for the standard deviation as well. Well, because this was empirical probabilities, based on the raw data up above, you might have an idea what the answer is going to be, but just in case, let's see here. We had scores from 1 to 10. And then our probabilities were 0.13, 0.31, 0.30, 0.1, 0.08, 0.01, 0.03, 0.01, and again, and a 0.02. So we do score times mean, score times probability, so equals, and then net multiplication. Drag it down to get this for all the rows, and then get the sum of all the rows in that column. sure something here. Getting 3.09. That matches up with what we computed from the raw data. And so now we're asked for the standard deviation. Take each score minus that mean of 3.09, square it, multiply by the probability associated with that score. And depending on how exact it needs to be, you can drag that column a little bit, then fill down, get our sum for that column. This gives us the variance. Once again, you've baked in the repetition and the total of the, what was it, 100 surveyed. That's all baked into those empirical probabilities. So no division is needed. Once you've got the variance, take the square root of that. And there is our standard deviation. They want this rounded to 3 places. So 1.844, it's rounding down. And I believe that should be the same as what we found previously. Oh, that's interesting. Okay, it's not. It's because we treated this as a sample, whereas now and so these were coming from empirical probabilities, but we're treating this by using the formulas for mean and standard deviation of a discrete random variable. Then we're treating this as if those were theoretical probabilities. Okay, what is the probability of randomly selecting an individual whose number of credit cards is more than 2 standard deviations from the mean? Well, our mean was 3.09. Let's do this. We're going to try this without any rounding. So more, 2 times more than, yeah, let me double check this. More than 2 standard deviations from the mean. So I didn't do any further rounding besides what the calculator already had. So what would be the probability that they have more than 7.09? That means they have more than 7. They have to have 8, 9, or 10. And one person surveyed at one time is only going to answer with one number. So the score of 8, the score of 9, the score of 10, you've got mutually exclusive events. We can just add these up without any double counting to worry about. No subtraction necessary. For probability of 8, 9, or 10, add up 0.01, 0.01, and 0.02 for a total of 0.04. Okay, let's see what happened. Okay, I've just typed this into my calculator with the rounded versions. The 3.09, well, that wasn't rounded anyway, if I remember correctly. But if I take that rounded standard deviation of 1.844, I'm getting 6.778, meaning having more than that many, we should be including having 7 of them, not just 8, 9, or 10. So I'm going to add 0.03 to what I previously came up with. 0.07 then. Can't see it. 0.07. Okay, now that's good. And is this an unusual event? That is not less than 0.05. So is not unusual because the probability is greater than 0.05. And what else is there? It's the probability of selecting two individuals who are issued exactly two credit cards. Are the events independent? Interpret the results. Interesting. So first off, exactly two credit cards for an individual, that was 0.31. Because the survey was conducted, I'm assuming randomly, then that should point towards independence. And double check that number, 0.031 for exactly two of them. Sorry, not 0.031, 0.31. So we want the probability of A, the first person has exactly two credit cards, and event B, exactly two credit cards. The probability of A and B, because of the randomness, should be pointing towards, yes, these are independent events, that how many cards one has does not affect how many the other card, how many cards the other person has, and vice versa. So I should just be able to square 0.31, and I'm getting 0.0961. They want that rounded to 3 places. So if they had selected two of the individuals randomly over and over again, we would expect, since that number was 0.0961, if you multiply by 100, 9.61, Part D is out because we wouldn't have independence. If they're a couple, then they're going to be affecting each other in terms of how many credit cards they have. This was not talking about an individual. So it seems to be down between A and B. Can't put in 9.61 unless they were to mention an average. So I think they're looking for 10 here. All right.